Good afternoon, everyone. Mr. Bencharsky here again today. We are going to be going into our final mini lesson for our unit on continental drift, which is part of our big unit on the Earth's crust. So we did volcanoes, we did earthquakes, and then we did continental drift. And after this, we're going to do a little bit about sort of the history of our planet and how we date things like that, how old our planet is, etc., etc. But today we're going to be looking at what's called the theory of tectonic plates. So if you're doing this lesson, you should have already have done the continental drift introduction and then continental drift reborn, because this is the final one that ties all three of those together. Now, so this is what we already know about our planet. Just like this egg, which if you cannot see, it's cracked unbelievably. The Earth's shell or crust is cracked into many small pieces. So as we learned in our last lesson, underneath the bottom of the ocean, when scientists started using sonar, they discovered that the bottom of the ocean had the world's longest ocean mountain range, which we call ridges, and massive caverns that go deep into the Earth's crust called trenches. And these mountain ranges or cracks of volcanoes and also where earthquakes occur, they stretch right across the whole planet and split our planet into big, what if you want to call them, pieces or puzzle pieces, some bigger, some smaller. We call these pieces, oh, my camera decided to go down, hang on. The camera's really not working with me well today. I apologize. I think it was the video on continental drift where like the whole camera was off and some of the answers were not visible. I apologize if you had trouble with those. So the second thing we know is that we call these pieces of the Earth tectonic plates. So when the very first lesson, when we talked about earthquakes and someone said, well, it's tectonic plates moving around, that's right. And the Earth is filled with them. These big puzzle pieces of our crust are called tectonic plates. And as you can see, there are some larger ones, some smaller ones. Because tectonic plates sounds better than puzzle pieces. Makes scientists think they're smart, which they are. There are 13 main plates covering the planet. So we have the Eurasian plate here in green. We have the Australian plate, the Pacific plate, the North American plate, the Nazca plate, the South American plate, the Arabian plate, the Indian plate, the Antarctic plate, and we have some smaller ones like the Caribbean plate, the Cocos plate, the Juan de Fuca plate, the Philippine plate, etc. Can you name the 5 largest? So on your sheet, I believe it asks you to do that. And I'm not going to give you the answer. I'm going to get you to guess here. What do you think are the 5 largest plates looking at this map? And if you're close, I'm going to give it to you because some of them do look slightly the same size. So pause the video and decide which one you think. These plates are made of both continental crust, land, and oceanic crust, land. So all of these plates, for the most part, have part of it that's land and part of them that goes into the ocean. Okay? So almost all of them have what's called continental crust, which is they're part of a landmass, and almost all of them also extend to under the water. Now, can you find one plate here that is all ocean? That is all ocean. That doesn't cross any continents or any land masses. There is one. So pause the video, see if you can find it. And can you name one that's made up of oceanic crust and continental crust, which means it goes over land and also over oceans? There's a few of these. This is a lot easier to find. Sorry, I still think it's a little off there. There we go. Now, the fourth thing that we know is that these plates are moving very, very slowly. They move about 3 to 5 centimeters a year. So if you think about that for a second, 5 centimeters is roughly the size of your fingernail, essentially. So they move about the distance of half your fingernail to your fingernail every year. So you can imagine that for them to move from the center of the Earth to where they are now would have taken millions of years. And the reason we know this is we've been measuring the movements of the continents for about 50 years now. So we know, generally speaking, we can predict where they're going to be. So that's about as fast as your fingernail grows. Your fingernails, I mean, depending on who you are. My mom used to always tell me when I was young, the way you know you're healthy is if your fingernails are growing. She was actually wrong about that. But your fingernails should grow about 5 centimeters a year, which is, again, that's how much the plates move per year. So Alfred Wegener was right all along, as we talked about in our last slide presentation. Now, we can measure how fast they're moving by using satellites in space and GPS stations on Earth. So like I said, for about the last 50 years or so, we've been slowly tracking the movements of these continents to know kind of what direction they're moving and also how fast they're moving. And we can make models and predictions of where they're going to be, say, in 100 years, 500 years, a million years, etc. Now, number 5, whenever the edges of these plates rub together or collide, they cause earthquakes, volcanoes, and mountains. So yes, depending on where and how they're moving, they cause one of these 3, 2 of these 3, or sometimes all of these 3. So sometimes when these plates come together, they cause earthquakes. Now that's what we're seeing right here in California, where the star is. The San Andreas fault line is causing it causes earthquakes all the time, all the way up here into Alaska. Sometimes volcanoes pop up right along these. We see this a lot in the Pacific. And in some cases, there's mountains, for example, like in the Indian Plate. So you can see there's all the edges, and where those edges meet, we get earthquakes, we get mountains, we get volcanoes, and sometimes, in many cases, they're underwater, so we don't see them. Now, let's just take a guess here, and we're going to look at Canada. Why do you think there are no large earthquakes or volcanoes in the town of Fredericton? Now, Fredericton, the capital of New Brunswick, is right over here in this star. Now, if your guess was that Fredericton is nowhere near a fault line or a boundary, yes, that's why. You're not going to get earthquakes and volcanoes popping up randomly in places like Fredericton. Paracutin, however, which is right here, right on a fault line, it wasn't shocking that a volcano popped up there. It's not shocking that California and Alaska have seen volcanoes and earthquakes pop up because we know exactly where they're located. Now, why do you think they have so many earthquakes in Presidio, which is also part of San Francisco? Well, because they sit directly on a fault line. Now, plates can rub or bump together in 3 different ways. So when we think about plates colliding together, there's actually 3 things that can happen here. One is called a divergent boundary. Now, divergent simply means they're going apart. So in these cases, when the plates are pulling apart from each other, a number of things happen. First of all, it opens up space for other things to appear, like volcanoes. Now, this happens on the bottom of the sea floor at places called ocean ridges. So underwater, those underwater volcano chains and mountain chains, these plates are pulling apart, and volcanoes, mountains will start to come out. New crust is being created at the divergent boundaries, so that's why we call it seafloor spreading. When the rock cools and the volcanoes erupt and all that lava cools, the rocks push the old ones away, creating new crust. That's why the crust at the bottom of the ocean is very young around those ridges, very old near the continents, and it pushes the old crust, like the continents, away. Now, the second type of way that these plates interact with each other is called convergent boundaries. Now, these are where these plates actually bang into each other. So you can imagine what happens when these plates bang into each other. The first thing that happens is old crust is destroyed when this happens, when these plates collide, and they can create volcanoes or earthquakes or mountains. Sometimes when these crusts collide, they push the rocks up, creating mountains or volcanoes, and in some cases, they just bang against each other and cause the earth to shake like crazy. Now, the last one is called a transform fault, and these are where the plates are actually sliding past each other. They're not pulling away, they're not going into each other, but they're going in opposite directions of each other. And this is the type we see in California with the San Andreas fault line. Now, these create earthquakes and mountains, such as the San Andreas fault in California. Now, the San Andreas fault line is such an interesting fault line because we can see it. Like you can literally see where it is. We've been tracking the movements of it for a very long time. We're going to talk about this for a second because this is kind of interesting, especially if you're a Canadian. Just because there's a little random fact here. Sorry, I'm having trouble with this camera again here. See if we can get a focus. There we go. Now, the San Andreas fault line cuts right through the state of California. So here's California, and you can see this green line. It goes right through California. Okay, splitting it, not in half, but splitting it. Now, the Pacific plate is moving westward or northwest, while the North American plate is moving in an opposite direction. This is actually a satellite image. You can actually see the fault line from GPS in space, or even from an airplane. Now, the San Andreas fault in California will eventually cause Southern California to break off and move north to Canada. So if you want a cool little thing here, here's Disney World right here. You can see right here. And if we want to go over time and fast forward, eventually part of it is going to break off right here and start heading its way north to Canada. Here's BC. Okay. Now, this is going to take millions of years, so I don't know. We're not going to be around to enjoy the fruits of having Disney World in Canada. And by the way, all of the shaking and earthquakes will destroy it anyway, but kind of an interesting fact about it. Now, number 7, one of the last things that we know is that a Canadian scientist was really at the forefront of determining these plates and how they move. And his name was J. Tuzo Wilson. And he discovered transform faults in 1965. He also discovered what were called hotspots. His work was vital to the overall theory. So he was the one who really looked into transform faults. At the time, we just sort of knew about the two types, but we didn't really know that there were also faults pulling away from each other in different directions. Now, we still don't know some things, and that's what scientists are working on as we speak. The first thing is we're not completely sure what causes these plates to move, which is still why this is considered a theory. So we know why the continents are moving, okay, because new crust is pushing them. But we're not exactly sure why other plates are moving the way they are, especially transform faults. Our best guess is that circulating convection currents deep inside the Earth slowly push plates that are floating on top. So our best guess is that in the mantle, the second layer underneath the crust, there's movement there, what we call currents. Think of ocean currents, but with magma. And as these currents move around, it moves around the crust sitting on top. Again, it's a best guess, but we're not 100% sure. This sounds like a good idea, but yes, currently speaking, we don't have a way to prove it. So maybe in the future. Now, as a bonus question, I want you to think about this for a second. This is a side of a cliff. Okay, so I don't know if you can see, but there's actually a guy right here. And he's got a large ruler sticking out of his hand here. Now, this is the side of a cliff, and these are dinosaur footprints that are going on the side of the cliff. Now, dinosaurs don't walk on sides of cliffs. So if your answer is going to be, well, maybe they did, they didn't, okay? But I want you to tell me, how do you think this could have happened? How did dinosaur footprints wind up on the side of a cliff? Think about that. And even though it is bonus, I want you to do it because I am going to count it. Now, this coral reef was lifted more than 5 feet out of the water when two plates collided during an earthquake. Okay, so this is a coral reef that really shouldn't be above water, but it is. But because when two earthquakes collided, it forced it up to the surface. Now, scientists also discovered new forms of life at the bottom of the ocean, living off energy from volcanoes in complete darkness. We talked about this a little bit when we looked at Challenger Deep in the beginning of the ocean. Beginning of our unit. But we are wrapped up here, guys. So once you're finished this note-taking guide, you can submit that to me. Next thing is we're going to be looking at sort of just how old our planet is, the history of the Earth, a little bit of that. There's a video to go along with that and a project at the end, which you will be doing in groups of 5. Otherwise, guys, talk to you soon. Bye now.